Let's discuss ensembles learning and random forests. And the first thing that we want to discuss is something called bagging. And you should be aware that random forests are discussed here is mainly because it is one of the ensemble model, learning methodologies. So what exactly is ensembling? Ensembling is the process of combining multiple models together to form a single model that is more accurate than its individual parts. The concept is that the mistakes of each individually imperfect but they're independent models will cancel out when the models are combined together. So in other words, you have multiple models and then you take some sort of average or majority voting to come back with your final conclusion. We will have specific examples that will follow shortly. For example, in regression model, what you do is you take the average of the predictions of multiple models output. In classification, you take the voted most common predictions. Let's take a look at this example. So suppose that you have your data here, and then you build a one model that is logistic regression, and then come back with a classification model to see which part belongs to red, which part belongs to blue dots, that which part belongs to white dots. And then you can also come back with a SVM classifier as well. Do the same thing. Of course, you have misclassification rate. There's a chance that you make a mistake. And then you have a random forest classifier, which you don't know yet, but it's really built upon decision trees that we just studied. So you have all those three different classification mechanisms, and they are all diverse predictors. This is as you can see, that there's a chance that each individual methodology may come back with a different conclusion. And then, for example, for this node, maybe one of the approach says it's a blue dot. The other approach could say it's a white dot. And then some other approach potentially says it is a blue dot. So idea is now the ensemble prediction is really trying to combine all these diverse predictors together to come back with a majority vote type of scenario. See that the first model says when new instance, one point should belong to category 1 classification, right? Different categories, category 1. And then second model says this node should be this point, new instance or point should be classification 1 as well. But the third model says should be a classification of 2. The fourth model says it should be a classification 1, because 3 of the models says that this new instance should be classification of 1, so that at the end, that ensemble prediction is built upon the majority vote of those 4 says this new instance should be classification of 1. So this is something called ensembling, and this is in classification space, right? For in regression space, it's just very similar, except that instead of using majority vote, you could use weighted average or just average itself of your predicted value for each of the regression methods. Now, question is, why are we learning about this? One of the key reasons is a lot of the methodologies could be combined to make it even more powerful. In cargo competitions, there are a lot of the models are actually ensemble methods that would be able to win the cargo competition. So for ensembling to work really well, the models must have the following characteristics. It has to be accurate, and then if they are independent, that would be even better. In other words, each one of this model, their predictions are generated using different processes. Okay, and then let's look at how this can be done. This hard voting process can be done in scikit-learn. So you could import random forest classifier, voting classifier, logistic regression classifier, and support vector machine classifier as well, SVC. And then for each one of them, you could define log on the cell F being logistic regression, and random forest RND on the cell F being random forest classifier, SVM cell F being support vector machine classifier. And then you define something called a voting classifier. And then this voting classifier comes from those three different types of classification methods. And then you use the voting equal to hard. For now, just remember that the way that hard voting equal to hard essentially based on the classification that we already come back based on the majority voting. We're going to discuss shortly about how this voting equal to hard can be relaxed using some other methodology. And then you use voting underscore CLF that fit to fit the X train and the Y train. And then, as you can see, we already have three different classifier and then one ensemble method, which is a voting classifier. So essentially it has four. And then what we want to do is let's look at each classifier's accuracy on the test set. And based on the test set, running through all four types of classifier, and then based on the test data set, you can see that logistic regression has 0.864 accuracy, random forest has 0.896, support vector classifier has 0.888, and then turns out to be voting classifier has even higher accuracy. Why is that? It's just because each individual model is predicting one observation differently, and then with the hope that when they combine together, then some of the inefficiency or deficiencies of the model's components can be canceled out so that the voting classifier can even do a better job. So that's really the purpose of ensembling. Now, there's something called soft voting. So what we just discussed is one model comes back, says this new instance belongs to classification 1 or classification 2, class 1 or class 2, right? If all the classifiers are able to estimate class probabilities instead of giving me a class categories, in other words, if they all have predict underscore product method, then you can tell scikit-learn to predict the class with the highest class probability averaged over all the individual classifiers. So this is called soft voting. So instead of coming back with a class category 1, I would say that there is belonging to class 1 with 0.98 probability. So instead of using this class 1, we use that probability and then combine all those probabilities together from different classifiers. As you would imagine, right, at the end, this 1 would still be 1, but it attach the specific probability. Now this is called soft voting. So all what you need to do is replace that voting equal to hard with voting equal to soft. Replace this voting equal to hard to soft so that you would come back with a soft voting ensembling method. So that's one way to think through. So you have multiple different models. It could be classification models, and then you take the voting mechanism. If it's all regression methods, you take the weighted average of the regression output. So what we just discussed is you could have multiple models of ensembling, but it is an alternative way. The other alternative way would be something called sampling. And even in the sampling, you would have two different categories of models. One category is called bagging or pasting. The other category is called boosting. So let's look at what exactly is bagging. Bagging says, takes a council of experts, give them each portion of the understanding of a problem, ask them to make a best educated guess at the solution, and tallies up the total solutions to make a final decision. That's bagging. And then boosting. Boosting says, takes a village of idiots, asks them one by one to set up to try to solve the problem. Each idiot picks up where the previous idiot left off and focuses on fixing the part that the previous idiot messed up on. So that's totally different methodologies, philosophies. If you think about bagging versus boosting, bagging is each individual expert is taking a subset of the problem and try to come back with educated guess, right? But boosting is more like, okay, someone just build a dumb model and then I try to improve upon that, and next guy try to improve upon this as well, so on and so forth. Let's look at in technical terms. Bagging. Of course, we also have a pasting. It's really not too much difference. I'll discuss shortly. It's also known as the aggregation of bootstrap samples. Trains multiples of the same type of model, for example, decision trees, using bootstrap samples drawn from the training dataset and combine the prediction results. Again, for regression, you use average. For classification, you use voting. When the samples are taken out with replacement, it is called bagging. When the samples are taken out without replacement, it is called pasting. So you should be aware the difference between bagging and pasting. More or less, they are the same thing, just trying to take different samples. And then if you don't have a replacement, then you call it pasting. If you do have a replacement sampling methodology, then it's called bagging. And then what's the difference between bagging versus boosting? Let's look at boosting again. It uses weak learners, typically decision tree classifiers, to build a forward stage-wise additive model that applies the weak classifiers one by one to repeatedly reweight the versions of the data so that each new weak learners to correct the error of the previous learners. So that's the idea of boosting. Just build upon the weak learner's weakness and try to improve it. Let's continue with the bagging. So bagging essentially says, okay, I have the original data set. I'm trying to sample some, not all of them, and then come back with a bootstrap sample 1. And then I could have bootstrap sample 2, sample 3, all the way to sample t. And then each one of them would build a decision tree model. And then at the end, I try to ensemble the results of all these T different decision trees, come back with results, right? So that would be something called bagging. And here you can see that it just says, okay, these white dots would be some samples that's removed. It no longer exists from the original data set. And then this red are the repeated samples from the examples from the original data set. So that's bagging illustration, just conceptually what it is. Same thing, essentially. We have a training data set. We didn't use all of the data set. We use a subset of it, sample, right? And then we use a different subset, use a third different subset, and fourth different subset. And then we do this random sampling with replacement equal to bootstrap. That's actually says essentially in the code, when you take bootstrap equal to true, it would be bagging, right? If bootstrap equal to false, essentially it would be pasting. So that's the difference between those two. Now let's look at how you can implement that in scikit-learn. You use a bagging classifier, you have decision tree classifier, and in your bagging classifier, you could pass in the decision tree classifier with 500 decision trees. So I have 500 different samples, and then max samples equal to 100. Meaning each of the sample size from the original data set is only 100. Max samples would be 100. And then you use bootstrap equal to true and n jobs equal to -1. And then you use bag underscore clf dot fit x train y train to train the bagging classifier. And then you can predict your y based on your trained model dot predict using your new test data set to predict your y. That's the implementation for bagging and pasting. You just need to replace this bootstrap equal to true or false to as a toggle to switch between bagging and pasting. Let's look at this chart. On the left-hand side, it's just a decision tree. You can see the boundary is kind of wiggly and trying its best to fit some of this data. And as we said, right, there is a chance that decision tree sometimes can overfit the data. However, if you do bagging using what we just discussed, taking certain number of samples and build 500 decision trees and then aggregate the results. And then you can see on the right-hand side, the decision tree with bagging, the decision boundary is much smoother than what we have on the left-hand side. And it's actually doing a decent job to separate the yellow circles to the blue squares. Just as we just said, right? Because bagging itself is a sampling methodology. So with bagging, some instance may be sampled several times for any given predictor, for any given predictor. However, others may not be sampled at all. So in that case, we know some of them are not sampled. The good thing is we can use something called out-of-bag evaluation in scikit-learn so that you would be able to come back with a out-of-bag score for all those observations. So you can set OOB underscore equal to true when creating a backend classifier to request automatic out of bag evaluation after the training. The following code demonstrates this. The resulting evaluation score is available through the OOB underscore under variable. So let's look at the code. Use backend classifier, again, passing the decision tree classifier into the backend classifier. And then you have 500 decision trees. You use bootstrap equal to true and OOB score equal to true. And then after you define this, you can fit train extreme versus Y train. And then you can come back with OOB underscore score, which is OOB score. Turns out to be 0.90. So according to this OOB evaluation, the backend classifier is likely to achieve about 90.1% accuracy on the test dataset. And then let's verify this. So you can leverage this prediction of X test and Y prediction. Based on X test, you can get the Y prediction, and then you can leverage accuracy score to compare Y test versus Y predict. Turns out to be around 91.2, so which is very close to the 90.1 number that we just got. So they're very close. So just different ways to look at the out of bag score. So what we just mentioned there was we used two different hyperparameters just now, right? So when we do the sampling, the observations or instances is controlled by two hyperparameters. One of them is called max sample, number of samples that you want to take out for the specific decision tree in this example that you want to build. And then the next thing that you want to adjust for the bootstrap, you want to use sampling with replacement or sampling without replacement, essentially bagging or pasting. There are two other things that you could be leveraged. That is sampling the feature. So just be aware of the difference between those two. The first one says sampling the observations. So you have a bunch of observations, maybe 10,000, but every time you only take out 100. This is exaggeration. Let's assume that you have 1,000 observations. Each time you only take out 100, sampling the observations, right? And then there's another way that you could be sampling the features as well, which would be the variables. You have 20 variables, but every time you only take out 5. That's called max features. And then here should be bootstrap features. And then second thing would be, do you want to do the bootstrap features as well? Do you want to bootstrap those features with replacement or without replacement? So that's different, right? So this part we're talking about sampling the observation. This part we're talking about sampling the features or random variables that we have in the data. And it's slightly different. If you sampling both training instances, observations, and features, this is called random patches method. You're doing both. Or what you do is you keep all the training instances, but sampling features only. So what you do by keeping all the training instances, you bootstrap equal to false and max samples equal to 1.0. But you could do setting the bootstrap features to true and max features to value smaller than 1.0. so that way you would be only sampling the features. So this method is called random subspecies method. So just pay attention to those two. You could leverage both. Okay. Now, after we have this discussion, we want to introduce you what is random forests. Random forest is an ensemble of decision trees, generally trained via the bagging method, or sometimes pasting, typically with max underscore sample set to the size of the training set. Okay, so let's look at what's on the left-hand side. You could, essentially, this is what we saw just now. You have 500 decision trees, max sample equal to 100. This is one way, which is passing the decision tree classifier to the bagging classifier. There is a different way, which is just leverage random forest classifier directly. In random forest classifier, you can define number of trees, and then you can even define max underscore leaf nodes to be 16, which is a knob for the decision tree itself, if you remember, right? And then you can fit X train and Y train to come back with this random forest fit, and then you can use random forest fit predict function to predict on the test data set. That's random forests. So now, conceptually, you should understand what are random forests. Random forests is ensembling methods based upon decision trees, usually leveraging bagging methodology. And then another thing that we want to discuss here is feature importance. So you would be able to output each feature's importance. Let's look at the top right here. And then remember that we load that iris data, and then we could use random forest classifier. In this case, we build 500 decision trees, and then we want to see, we fit that data based on iris data and target. Basically, this is X, this is Y, and then we build a classification, right? Random forest classifier, classification method. And then what we want to see is for the name and score in zip, iris feature names and random classifiers feature importances to come back with the score. So it turns out to be petal lengths and petal width have higher score comparing to the sepal lengths and sepal width. If you recall, when we built the decision tree model, decision tree classification model on iris data, we only take out these two, purely just because we already know, which of course, if you don't know this data set, you would never know. But we already know that these two have higher importance, so that it's a better illustration to plot that decision tree based on those two specific dimensions. Of course, if you pass in all of the data, the conclusion would not change just because of the importance of each feature. So similarly, let's look at this chart on the bottom. In the MNIST pixel importance, which is based on random forest classifier. So what is this image is telling us? This image essentially says that if we want to understand the handwriting of all those numbers that we discussed in previous chapters, then where are the most important regions. You want to make sure that they are written clearly. As you could imagine, right? Number 2 might be showing somewhere here. That's why it's more important. Of course, number 8 might be slightly different. Number 6 would be slightly different. Number 1 would be slightly different. But overall, you can see that these regions are much more important compared to other regions from the outside. So the feature importance of all these pixels can be defined. That's a very powerful conclusion, right? So, that's something you should be aware. Okay, so this actually concludes our discussion on bagging, and then we'll come back to talk more about ensembling methods. Thank you.